All right. '81. So we have log of the fourth root x over y. And we're supposed to be expanding here. So Mia, what did you try to do first?
My final answer was 1/4 log x minus -1/4 log y.
Okay. So yeah, as it's currently written, you couldn't do the quotient property first. You'd have to do the power property first because the power is around the quotient. So if you wanted to, you can do it this way. And then when you apply the quotient property, you have to make sure that the result is also being multiplied by that 1/4. So I think what you read to me is correct. Alternatively, in the beginning, you could have used your exponent property to rewrite it this way, and then you could do the quotient property first and the power property second. Either of approach is a fine one. Yeah, totally fine. That's what the question time's for, right? Jack.
Number 104.
Sure. Oh, excuse me. Okay. 104 says 3 times 5 to the negative x over 4 equals 15. So first step would be to divide by 3. And here I would just use the one-to-one property since the base of the exponential is the same. I can just set the exponents equal to each other. Alternatively, you could have done log base 5 to both sides. That'd still be appropriate. But, you know, it's like swatting a fly with your Encyclopedia Britannica. It's a little bit overkill. You know what I mean? Making jokes here, guys. It's supposed to be funny. It's okay to laugh. Or not if it's not funny, you know. But I'm trying. Who else? Yes, Amanda.
Can you do
125? Yeah, sure. So we have 500 over 1 plus 25e to the 0.3x equals 200. Okay. First thing I notice is the location of the variable. It's in the exponent and in the denominator of the fraction. So I'm going to take care of the denominator of the fraction part first. So I just do like a cross multiply thing. Is that cool? Divide both sides by the 200. And I reduce that as I went. I hope that's okay, right? Okay. And then we'll subtract the 1. And like I made the common denominator and subtracted as I went. That's okay? They're easy fractions. I just want to make sure I say something because at first glance you're like, wait, what? It's okay. And at this point, I would then do log base 25, or I'm sorry, nope. I lost my E somewhere. There we go. Forgot that E in there. That's a big oopsie. Now I need to divide both sides by 25. Again, I did the arithmetic. You're good, right? Okay. I feel bad. I have to say something. And then we natural log both sides. And then we'll divide both sides by 0.3. I'm going to write it as multiplying by a reciprocal so that I don't confuse myself as to whether that divide by 0.3 is inside the logarithm or outside the logarithm. If I write it that way, it's like super duper clear where that thing belongs. But that's just what I like to do. But like communication in mathematics is important. So I get negative 0.37, or let's call it 0.38. Wait a minute, that's not what I wrote. What did I write? Oh yeah, that's okay. And does that match what we're supposed to get there in the back of the text? Did you look at the odds there, Amanda? You look real quick. Oh, good. Yes, that is correct. You always sometimes you do them and you're like, yeah, that's got to be right. Is it? I was surprised they got a negative answer. Not that that's impossible, but it's a little surprised by it. But it's okay. Feel good?
Yeah.
So probably the biggest trick is just remembering to cross multiply in the beginning to get the x out of the denominator. And then from there, it's pretty relatively straightforward anyways. Who's up next? Anybody else? Others? Bueller? Alrighty. Let's rock and roll then. Okay. 15.4 continued. What we're going to be looking at in the last half of section 15.4 is applications, like real-world applications that use exponential or logarithmic functions to describe them. And we'll use our solving skills that we kind of built up to answer story problems related to those. Okay? So we have like 4 or 5 situations that are kind of common exponential or logarithmic kind of situations. So the first one is sound intensity. So like loudness, how do we measure loudness? Decibels, yeah. So our equation here, or our model here, I should say, is beta equals 10 times log of I over I naught, where beta is the number of decibels. The symbol for decibels, just if you're curious, is lowercase d, uppercase b. You're like, wait, what? Well, the prefix for deci, that's the abbreviation for that is lowercase d, right? SI people. So that's why that's cased in that way. I is sound intensity. and that's measured in watts per meter squared. And I naught is a constant. That constant is 10 to the negative 12 watts per meter squared. So let's kind of look at an example. Given that the sound intensity of busy city traffic is approximately 10 to the negative fifth watts per meter squared, what is the measure of busy city traffic in decibels? So hopefully nobody's surprised when I say that we should be using our sound intensity model. Which parameter are we asked to solve for in the question? Beta, I, or I naught? Beta. Why? Yeah, it wants the number of decibels. Okay. So where does this 10 to the negative fifth go? That's the I. And what's I naught then? That's a constant. It's always 10 to the negative 12. So we'll just plug these in. So 10 to the negative 5th divided by 10 to the negative 12th is 10 to the 7th. Log of 10 to the 7th is 7. 10 times 7 is 70. Or you could type that into your calculator. You guys probably have heard of decibels before, right? If you watch sports games, they like to, oh, look at the fourth quarter, the sound in the stadium. And they show a little thing on the screen, and it's like, oh, it's as loud as a jet taking off. And you're like, yeah, sure it is. It's like I've been into a stadium before and it's not that loud. But, you know, whatever. Everybody cool there? Okay. Again, like, you could rewrite the question we're solving for a different parameter or whatever, but it's just, they're kind of, you know, it just is what it is. Another model is the Richter scale. What does the Richter scale measure? Earthquake magnitudes, yeah. So this is the Richter scale equation. And I'm going to abbreviate earthquake as EQ because that's a lot of letters. So R is just the magnitude of the earthquake. When an earthquake happens, like, what's really happening? So you have the ground at the usual level, and it's kind of going up and down, right? That's kind of how an earthquake works. So we have normal ground level, and the maximum displacement, either up or down, is what we're going to refer to as alpha. If we think about this as like, if we're moving up and down and we want to graph this over time, it's going to look like a what sine or cosine wave. So that maximum displacement up or down is really the amplitude, right? This is amplitude. And we measure this typically in micrometers. So that's the Greek letter mu that looks like the two-sided U or the funny-looking M, depending on how you want to look at it. It always looks like a U to me, but it's supposed to be the lowercase Greek letter M. It's the letter mu. I think that's 10 to the negative 12th. Is that right, SI unit people? I think that's right. T is the amount of time it takes to go, ground at base level, maximum displacement up, maximum displacement down, and then back to base level. In the parlance of sine or cosine, that is the
Frequency.
close. It's the period. It's the other one. It's the period. And we measure the period in seconds. And then the B, now when an earthquake happens, where is the earthquake the strongest at? The epicenter, right? And as you move away from the epicenter, what happens to the earthquake? It's less intense, right? So this B is like a correction factor because the tool that we have to measure the earthquake intensity isn't usually at the epicenter of the earthquake because you don't know where that's going to be, right? So this is basically just correcting for the location of your measurement. So it's giving you like the intensity at the epicenter. Right? Like if like the earthquake happens in San Francisco and your tool for measuring your earthquake is in like Sacramento or something, the earthquake in Sacramento feels like a 2.6, but you have to correct it because you're like 200 miles away from San Francisco or whatever. So in San Francisco, it's actually much, much worse, right? That's what the B is doing. It's like a correction factor based on the distance away from the epicenter that you're taking your measurement at. Does that feel okay? So we just kind of talked about some of these things. And I gave like a trig kind of definition for some of these, but all right, let's look at an example. The infamous San Francisco earthquake. I think we give it the title infamous because it's the most or highest magnitude earthquake on record in the continental United States. I think there's probably some stuff in Alaska that's been worse. You're sitting on that ring of fire, so I'd imagine that out in one of those remote islands or something right there on that Pacific plate, you get something pretty nasty going on, but we're talking only continental. Had a Richter scale magnitude of 9 or 7.5. How many more times severe was the most severe earthquake ever recorded? The 1960 Chilean earthquake had a Richter scale magnitude of 9.5. So, couple of things here. When we talk, it's asking about severity, right? And we look at these measurements or these factors we have, which one of these is measuring like severe, would describe the severity? If you're talking about like, be this part, right? The more that's shaken, the worse the earthquake really is. You guys buy that? So it's really the up and down when we're talking about severity. Everybody buy that? Now, we're not given any measurements in here other than the Richter scale measurements, right? And we're given 2 Richter scale measurements. What do you suppose we're going to have to be doing? Well, hopefully it should come as not too much of a surprise that this is going to turn into solving a system. Everybody's hopefully not too surprised by that. And since we're asking about severity, I know that the alphas here are definitely going to have to be different, right? We said that alpha is kind of our descriptor for severity. But now let's think about the B's and the T's for a moment. So we're given a Richter scale measurement, which is equivalent to the measurement that you would have at the epicenter, right? So since both of these are being measured essentially at the epicenter, the B's we can assume to be the same, right? Since whatever that correction factor was, it's already corrected, so it's basically a B value of 0. I'm going to just say they're equal to, and since they're both equal, I'm going to just call them both B instead of B1 and B2. What's the other piece of information we're not told anything about? The period, the T, right? We're going to make the same assumption that these T's are the same. And I think probably empirically that's pretty common, that if there's a bigger displacement, it just moves faster, so that period ends up being the same as if there's a small displacement and probably moves slower. But we don't have that information, so we're going to have to get rid of it somehow. We're going to just assume they're the same. Okay. If I call this equation A and equation B, I'm going to do equation B minus equation A. The reason I'm choosing to do that order is because I probably want a positive value on that left-hand side, so I'm going to take whatever the bigger one is and subtract the smaller one from it. That look okay? Well, first thing I'm going to do is I'm going to distribute that negative sign. So I can do that. Everybody's good? What do you notice I can do once I've done that? The B's cancel out, right? Righteous. So I'm left with log of alpha 2 over t minus log alpha 1 over t. What can I do with that? I'm going to use the quotient property to condense those since they're being subtracted. So remember, with logs, we really got to, if we have more than one log in a place, we're really going to be relying on those properties. And since both of these are fractions, when I use the quotient property, I'm going to write a division symbol in between them rather than a fraction bar, because I don't want to write like a yucky looking fraction on top of fraction. That feels both kind of yucky looking and like not particularly helpful for what I'm about to do, which is to ask you to remind me how I divide two fractions. Multiply by a reciprocal, right? Back in elementary school, they told me dividing fractions is easy as pi. Flip the right and multiply. And it must work because I still remember doing it, or still remember the little saying. And that's nice because what do we find there? The T's are, get out of here. Everybody feel good there? All right, what's next? Got to get rid of that log, right? How do I do that? Well, it cancels a logarithm. Exponent base. Which exponent base would I want to use here? 10. Why base 10? It matches the base of the logarithm. I remember when there's no subscript written on my logarithm, that is the common log, which has base 10. So what is this relationship saying? So the alpha 2 comes from the Chilean earthquake, right? So we can say that earthquake is 100 times more severe than the San Francisco earthquake. That feel okay to you guys? Trickiest thing was getting the system set up because of the assumptions you had to make. Once you had the system set, not so bad, right? All right. Next model we'll look at is acidity. How do we measure acidity, chemists in the room? pH. So remind me the pH scale. What does it run from? 0 to 14. Okay. And there are kind of three things, right? There's acids, there's neutrals, and there's bases. What pH measurements indicate an acid? So we'd say 0 to 7, like that. Notice I'm using like set notation there, so including 0 but not including 7. Neutral is 7. And then bases 7 to 14, right? Good job remembering. And then when I write a chemical compound, but I put the brackets around it, what does the bracket around it indicate? It means we're talking about the concentration. And how do we typically measure concentration, chemists? The molarity, which is moles per liter. You could use molality also, although that's pretty rare in practice, I think. It's amazing when it all circles back, right? It's like, I thought I was done with chemistry. Okay. So let's do an example here. Don't worry, you don't have to balance a chemical equation or anything in here. So, all right, a really sour lemon is found to have a pH of 2.2, and a bottle of bleach is found to have a pH of 10.2. Part A asks, what is the hydrogen ion concentrations of the two items? I always try to write these in red, don't I? So again, hopefully nobody's confused by me needing to use the pH model here, right? So for the lemon, we'd say 2.2 equals negative log of H plus. And then for the bleach, we'd say 10.2. equals negative log H plus. Cool beans so far? To solve those equations, first thing I should do is divide by -1 or multiply by -1 or just move the negative sign over, however you want to say it. Is all of those are fine. Then what? Again, we're trying to get the concentration of hydrogen ion by itself. So I got to use the exponent base 10 to cancel the logarithm. I'm going to skip writing some of the detail on that work. And then I'm going to go to my calculator. So I get 0.00631. I'm going to write that in scientific notation. You'll see why I chose to do this use scientific notation in a moment. Here's actually we'll say it right now. I chose to write this in scientific notation because a base can have more or less hydrogen ions than an acid. Less, remember the acid is the proton donor, the base is the proton receiver. So definitely going to have more hydrogen ions in the acid. If this is already a pretty small number, the base could be a really small number. So I'm just kind of getting out ahead of this and already going to write these in scientific notation because I'll probably want to do it on the other one. It's the same steps, though, to solve for the base or for the bleach, right? So I'm just going to skip down to here and not write any of the other work. Is everybody cool with that? If it's the identical steps. If you're not, you can tell me. And whoa, doggy, 6.31 times 10 to the negative 11th. And then for part B, I think there's an error in this. I think it should read, how many times greater is the hydrogen ion concentration of the lemon than that of the bleach, since clearly the lemon is more hydrogen ions. I think that was just a typo. So I would say, okay, well, if I ask for times greater, what operation are we going to be doing? Dividing, right? Like 4 is 2 times greater than 2, because 4 divided by 2 is 2. So if I do that, I'm going to get 10 to the 8th. Or if you're not, you're like, wait a minute, Mr. Kulak. Okay, you can do it on your calculator. You just do the lemon concentration divided by the bleach concentration. That is about 100 million. Wee woo wow. It's a lot of more ions, huh? Yay, chemistry. Cool with this one? Not a big deal, right? Our last one that we're going to look at is Newton's law of cooling. So what Newton's law of cooling describes is if you take a hot item and you take it out of the heat and you leave it somewhere, how does it cool down? Right? So if you guys have ever burnt your mouth on a pizza roll or something when you take it out of the oven and try to eat it too fast and you're like, my mouth is full of lava right now and I've burnt my tongue to death and I can't taste anything now, this might help, right?
So you can calculate how long it's going to take mine.
Yeah, we definitely could do some experiments and definitely do that.
It's totally recommended.
All right, so the T of T is the temperature. T minutes after removal from your heat source. So like after you take your pizza rolls out of the oven or microwave or whatever your preferred toaster oven, however you're making your pizza rolls. TM is the temperature of the surroundings. So like in the pizza roll example, the TM is just the air in the room, right? So room temperature or whatever. Now, if you're like a medieval blacksmith and you're pulling your sword out of the furnace and then you're doing like an annealing thing and you're dunking it in cold water, the temperature of the surroundings would be the cold water. I don't know if we have any future blacksmiths in the room, but so T naught is the temperature of the substance upon removal from heat. K is a constant, but that constant is specific to the substance. So for example, like your pizza rolls are going to cool differently than your, steel sword would. Not surprising. Probably we've made, tomato soup and a grilled cheese sandwich, and the grilled cheese sandwich is eatable way quicker than the soup was, right? The soup cools a lot slower than the sandwich. And the little t is just the time that your substance has been removed from heat, and it's in minutes. All right, let's look at an example. Okay, a hard-boiled egg is heated to 96 degrees Celsius and placed in a pot of water to cool, 16-degree water to cool. After 4 minutes, the temperature of the egg is 45 degrees Celsius. Find how long it'll take in total to cool the egg to a temperature of 20 degrees Celsius. So hopefully nobody's going to be confused by me wanting to use Newton's law of cooling here. Seems like a pretty obvious cooling situation. If I read this problem, I'm given a lot of information, but there's distinctly one piece of information lacking. What piece of information is not ever given to me in here? The K. In no point are we talking about the constant of cooling for an egg. So what we're going to do is, like, the first part of this question gives me information about a specific situation. We're going to use that specific situation to solve for K. Once we know that K, then we can answer the actual meat of the question. So this is going to be kind of like a two-part question. Okay? All right, so let's start figuring out where we're going to put things. Where does this 96 go? That is the T naught. That's the temperature of the substance upon removal from heat. Good. What is the 16? So we took the hot egg out and we dumped it into 16-degree water. That's the TM. Okay. 4 minutes tells me, hopefully nobody's confused that that's little t. So the 45 degrees must be the T of T. Okay. Well, let's solve here. What's the first thing I should do? Subtract the 16, that's good. And then 96 minus 16 is just 80. I'm going to go ahead and do that arithmetic at the same time. Everybody's cool? Next up, divide by 80. Yep. Next, natural log, very good. We got to use a logarithm to cancel the exponent base. That means we need to use log base e, or the natural log. If you had written log base e, that's okay. If you type into your calculator log base e, the calculator still knows what you're trying to do. It'll be fine. It's the same thing as the natural log. And last step then is to divide by -4. Again, I'm going to write that as multiplying by the reciprocal, so there can be no confusion about whether that dividing by 4 is inside the log or outside the log. If I write it that way, I don't have to be quite as careful about how I'm kind of writing it down, so as not to confuse anyone. So we get about 0.254. So again, the yellow part of the question we've just done here. All right. Time to do the green part now. It's asking us how long, so what are we solving for? Little t, right? Good. And it says, how long will it take in total to cool the egg to a temperature of 20 degrees? So what is the 20 degrees? That's the T of T. Have the temperature of the surroundings changed? No, man. Has the initial temperature changed? No, man. The only thing that has changed is now we know the K is about 2.54. Oops. Forgot to write my E. And now it's kind of the same problem that we did last time, right? First step would be subtract that 16. Then we divide by the 80. Notice that could reduce, but I'm not really interested in it because it's just going to be a calculator question in a minute. So like the calculator can handle the reducing. I don't care. You know what I mean? If you want to reduce, that's fine. But like, who cares? Then we'll natural log it. And then divide by the negative 0.254. And I'm going to be a little bit careful here because I'm going to use my whole decimal point here for the K when I type this into my calculator. So I get about 11.81 minutes. Or I guess what's that in time? What's that, 49 seconds or something? Yeah, there we go. Or about 49 seconds. You don't have to do the seconds thing, right? So 11 minutes and 49 seconds, or 11.81. I'm just pointing it out here because, like, if this is an ACT question or something, they'd probably write it in minutes and seconds. You know, but that's the gist of it. So again, this one a little longer than the previous ones, but mostly because it was kind of like a two-part question. But not too different than the solving that you did yesterday with no context to it. But like once we have the equations written, it's kind of the same as the problems we saw yesterday. At this point, you guys can now be able to do up to 138. I'm going to stop here today. I know it's a hectic, busy week for a lot of us with the AP stuff, so I don't want to go too overboard. So this is where we're going to stop today. Sound cool to you guys? Okay. You guys have, I don't know, with 30 minutes or so remaining, you guys can work on your math stuff or whatever's the highest priority item for you.